All right, let's start to talk about waves. Hopefully, you should see very obviously that there are two types of waves we're going to begin to speak about. The first, of course, being transverse, and the second being what is known as a longitudinal wave. We'll get to the differences between these, and we'll talk about some examples of each. But let's begin with a transverse wave. That's probably what you're more used to seeing when you think of a wave. You think about a wave that kind of goes up and down and up and down. You've probably seen it in the ocean, maybe in a pool. Most common wave you've probably experienced in your daily life. Actually, probably not the most common, but the most common that you've seen. Let's go with that. The most common that you've seen. Longitudinal is a little bit different. Um, so for a transverse wave, it's important to realize one thing. If I have this wave here, well, let's go ahead and let's assume that our wave is traveling, let's say from the left to the right. So if our wave is traveling from the left to the right, that is the wave's motion. Okay, that's the wave speed. Well, let's take a look at an individual particle here. Okay, if this was a rope and I were making these waves, hopefully you can see that despite the fact the wave is moving from left to right, this individual particle is not moving from left to right. That section of the rope is not actually going to move from left to right. Well, if we take a look, in reality, this particle is actually just going to move up and down. Let me redraw this so you can see very clearly. That particle right there is going to be moving up and down. Okay, that section of the rope is not going to physically move anywhere other than up and down, and then up and down and up and down as multiple waves pass through this point. Now, one way that may help, if you can come up with your own method, that's fine. But what I like to say sometimes is, well, take a look at the particle's motion. The particle is moving up and down. The wave's direction, the wave speed is traveling in this direction. Wow, that kind of makes a T. I know, mind-blowing. T, transverse. That's one way you can remember it. If you'd like to just memorize them or just get familiar with them on your own, that is fine as well. If this helps, waves motion, particles motion, kind of makes a T. The important thing to take away here and realize, Mr. Walker, which is awesome at coming up with crazy analogies. You're welcome, by the way. The second thing is that for a transverse wave, the particles of matter through which this wave travels, they are going to move perpendicular to the actual wave itself. So they move perpendicular to the wave's motion. That becomes a really important concept as we move forward. We'll begin to talk about this more so when we get into light and some other things, but the particles are moving perpendicular. You can see this is a right angle here. Particles will move perpendicular to the wave's motion. Now, longitudinal. This, I want to be very clear, this is not like a transverse wave. This is a spring or a slinky, something along those lines. So please don't get confused. This would be a spring or a slinky. And what would happen here is if I took one end of the spring or slinky, and rather than moving it up and down in this direction, which would generate a transverse wave, the slinky would begin to move up and down. Well, instead of that, I actually take this end and I push it forward. So if I push that forward and let it come back, and push it forward and let it come back, what I wind up with are sections of this spring or sections of this coil that wind up being compressed. And that's going to compress the next coil in front of it, and the next coil, and the next coil. But after that compression passes, you're going to have these areas where it's kind of spread out. And if I had to repeatedly move this end back and forth, you get alternating areas of compression with alternating areas of like relaxed tension. Maybe it makes more sense if you look at maybe air molecules. And this is actually how sound travels. Sound is a longitudinal wave. So if I have something vibrating over here, it's going to begin to push the molecules immediately next to it. These molecules, these particles, are going to begin to press into the next one and bump into the next one, and the next one, and the next one. Well, if this were to stop vibrating momentarily, these compressions are going to begin to travel through the air molecules. And after each compression passes, you're going to have a section where they kind of spread out again. They go back to normal. They're not highly compressed. So if I were to continually vibrate something over here, you're going to wind up with alternating sections of compression and high pressure compression and areas of low pressure where there's not very much compression. That's a big thing to realize. Please, 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 somewhere in your notes. Transverse wave. Particles are moving perpendicular. Hopefully, it's not a giant leap to realize that an individual particle on this slinky is actually going to be moving in this direction. It's going to be moving back and forth. Okay, it's going to originally get pushed in this direction as that compression comes through, and then it's going to return and oscillate until it reaches its original point, its equilibrium position. So again, hopefully it's not a giant leap to realize that the particles in a longitudinal wave are not traveling perpendicular. They are actually moving parallel in this case. The particles are moving parallel to the wave's motion. It's also at this point, now looking back on my other definition, that it's very obvious to me that this should be the word moving. So anyone that caught that before and is now yelling and screaming about it, you can all leave me alone because I fixed my mistake. I apologize for those whose day I just ruined with poor grammar. Now, the next step, mechanical waves. What are mechanical waves? Well, the definition is already there, so if you couldn't figure that one out, we should read directions, as I always say. Mechanical waves. Well, what are they? They're waves that require a medium to travel through. Mr. Walkowicz, that is excellent. I now have a definition of mechanical wave. But what is a medium? I don't really know what a medium is. That's fine. That's why I made this video. Everything's going to be all right. Medium. Again, definitions down here. If you were a little bit lost, read. The medium is just the matter through which a wave travels. Okay, so can you hear me right now? I'll give you a hint. Sound is a longitudinal wave. It's a mechanical wave. Can you hear me? I think you can. If you can hear me, and it's a mechanical wave, that must mean there must be a medium. So if there's a medium, what would the medium from your computer's speakers, where the sound is originating, to your ears? What is that medium? If you said air, congratulations. Pat yourself on the back, give yourself a high five. If you did not, there may be or maybe not some future opportunities. We'll see. We'll see how well you guys do. Now, my video, my lecture would not be complete without one terrible joke at least. So, for your viewing pleasure, why couldn't the wave talk to, I apologize, why couldn't the mechanical wave talk to its dead relatives? Well, you may have already figured out you couldn't find a medium. It's hysterical, I know. If you can kind of recover, let's move forward. Waves are awesome. Now, wave characteristics. What does this mean? Well, we're going to start to talk about waves in incredible detail. We're going to talk about waves for this chapter. This chapter is entitled Simple Harmonic Motion in Waves, so I hope that does not come as a major surprise to you. But we will also continue our discussion of waves when we deal with sound and light, which will finish out the rest of the year. So you're almost there for all of you that hate physics. You're almost there. You've almost made it. Congratulations. For those that love it, I'm sorry it's coming to an end soon, but luckily there's the rest of your life to enjoy physics, so there's that to look forward to. Now, in order to talk about all these things, we're going to need to be able to kind of get on the same page in terms of how we're going to actually talk about these waves. What are the parts of a wave? How can we discuss this so that we're all understand what's going on and we're not all completely lost? Well, let's take a look here. Hopefully you realize that this is a transverse wave. And down here, what I'm representing with particles of air, let's say, are going to be a longitudinal wave. You have areas of compression and you have areas of no compression or areas of low pressure. Let's start with the transverse wave. That's probably one you guys are more familiar with. The first thing we're actually going to need to look at, let me get to the right page here. First thing we're going to need to look at is, what is this called? This distance right here is the same as this distance. It is also the same as this distance. It is the same as this distance, and so on and so forth. Hopefully, from some of our study of simple harmonic motion, some of our class discussions, I'm hoping that you guys realize that each of these sections, it's the maximum displacement. It's how far this wave is being displaced, or the matter at this specific location is being displaced from the equilibrium point. And that, of course, is referred to as the amplitude. The amplitude of the wave. So here we have amplitude. Some more basic definitions. Anytime you have maximum displacement above the equilibrium point, or we would say like a positive displacement, that's what's known as a crest. Okay, every location. So this is a crest, this is a crest, this is a crest. Hopefully that makes sense. Well, the maximum displacement underneath the equilibrium point, or like a negative displacement, so to say, that's what's referred to as the trough. So if you hear myself or anyone else refer to a crest or a trough or amplitude, you now know exactly what they're talking about. The only other thing we're really going to need to consider here, and this is something that sometimes really confuses people, and that would be, what is wavelength? Okay, well, wavelength is just start at one point, go through one crest, one trough, and return to the point you started. So if I were to start right here, Okay, for those that don't see it, I'm terrible at picking colors that don't look similar, so I probably should not use pink. I'll go with black. All right, so if I'm starting right here, okay, if this is my first point, I have to go through a crest, then through a trough, and return to the point that I started at. If I started at equilibrium, I should finish at equilibrium after having gone through a crest and a trough. So if I go from here to here, this distance is going to be one wavelength. And we refer to wavelength with the Greek symbol lambda. So that is one wavelength. Oh, but Mr. Walkowicz, what if we didn't start at equilibrium point? What if we started at a crest? Because that's a new vocab word, and I love vocab. Well, fictionary person that's asking me this question, let's go ahead and say we were to start from this crest and go to this crest. Well, we're at a crest, we go down through a trough, and we come up and cover the second half of that crest. So what I wind up with here is also the wavelength. Hopefully you're starting to see that I could also go from here to here, and this will be a wavelength. You essentially just have to go through a complete crest, through a complete trough, and wind up back at the same place you located. Not the actual same place, but at the same elevation, so to speak. So you could have multiple wavelengths. It doesn't matter where you start from. You can start from any of these points in between. You would just have to go through one complete trough, one complete crest, and wind up at the same location, or the same elevation, so to say. Longitudinal waves, not that different. Think of these compressions, these compressive areas, kind of like a crest, and these low pressure areas, kind of like a trough, but we actually give them slightly different names. Hopefully this is not anything that's mind-blowing, but these areas here, areas of high compression, they are just referred to as compressions. So hopefully that's nothing mind-blowing. Compressions. Now the other one doesn't make quite as much sense. These areas where you have low pressure, what would be the equivalent of a trough on a transverse wave, these are actually what are called rarefactions. The word rare and the word faction together, rarefactions. Okay, compressions, area of high pressure where all these molecules are forced together, rarefactions. After these compressions have passed through, you have areas of low pressure. And the only thing that's very similar here, well, if I go from an area of compression to an area of compression, it's just like going from a crest to a crest, which would give me one wavelength. So this here would be one wavelength. It would also be fair to say that from one rarefaction to another, the next rarefaction would be another wavelength. So they're fairly similar, the main difference being crest and trough versus compression and rarefaction. Now, lastly, do waves transfer matter? That is an excellent question. And the answer to that question, as I would say very eloquently, is nope, nope, never, nope, absolutely not, nope. And let's go ahead, and I like all caps, and I'm feeling green, because you know what they say, go green or go home. So let's make this bold, and I can't be any more clear than this. No. Let's just put a few of these here just to really emphasize this point. And you know what? I'm going to underline it in red so it stands out a little bit. Nope, pink, no red, I don't know. A different color, you get the point. Now, no. Why is that no? Well, let's take a look. As this wave is traveling this way, that's a transverse wave. Very good, whoever just called that out. Transverse wave is traveling this way. If I have a particle here, that particle is matter. That's an actual piece of matter. Is that matter actually moving left to right? Nope, moving up and down. So the matter itself is not actually being displaced. Okay, so if matter is not being displaced, then what is actually being displaced? Gee, Mr. Walkowicz, you have so much energy as you describe this to us. Thank you for catching the point. Ladies and gentlemen, waves do not transfer matter. Waves transfer, I really hope you got it from my second terrible joke, waves transfer energy. And it kind of makes sense when you think about it. Think about a wave, let's say like a tsunami. You have an extremely massive wave. That's not actually sending all the water in the ocean towards you, but it's transferring energy. Okay, so the energy is what a wave transfers. And as to the analogy I just gave you, well, we have a tsunami. Most people are afraid of tsunamis, rightfully so. Imagine the amplitude of that tsunami. It's huge. Okay. Take a smaller wave. You're standing in the ocean. Small waves are lapping up against your legs. You're enjoying, the nice weather. And you're not really feeling any kind of effect. There's not a lot of energy. So you need to realize here that the amplitude, okay, the amplitude of a wave is going to measure the amount of energy that that wave has. And it makes sense when you think about it. Okay, if you saw a wave rushing at you that had an enormous amplitude, you would probably be terrified of that. The amount of energy that's rushing towards you, as history has shown us, a tsunami has enough power to essentially wipe out cities. The amount of energy that is associated with that amplitude is extremely high. But we're not really terrified of small waves that lap in on the ocean or lap in on the shore because the amplitude is so small. They don't have a lot of energy. All right, so quick recap. Transverse, longitudinal waves, please know the difference. Mechanical waves. There are other types, mainly electromagnetic waves, which would be something like light, but we'll get to that when we talk about light. The important thing to realize, mechanical waves require a medium through which to travel, and the medium is the actual matter through which the wave travels. If you're sending a wave through a rope, the rope is the actual matter. That's the medium. You can hear me right now. Sound is a mechanical wave. It must be traveling through the air. If you were to yell underwater, you would hear someone because the water is the medium. If you were to go to outer space, you would hear absolutely nothing because there is no matter in space. That's why it's called space. It's a vacuum, and that's why nobody can hear you scream in space. So enjoy the nightmares that you have tonight. Again, not going to go through all of this again. Just realize crest, trough, compression, rarefaction, amplitude. Just be aware that this is the terminology we use, and the rest of the year will become easier and easier the more that you understand these concepts. And last but not least, waves do not transfer matter. If you take a look at it, as I said over here, the actual particles themselves, they move up and down. They're not moving left to right. The waves actually transfer energy. You move your hand on one end, your hand has kinetic energy. That kinetic energy is being transferred through the medium via a wave. And if you want to know how much energy a wave has, look at its amplitude.